In this video, we're going to talk about tension. Now, tension is just a fancy way of talking about forces that are applied using ropes. If you are pulling a box with a rope, then we might say that there is some applied force coming from you, but it's more appropriate for us to label that force as tension and use the letter T instead. Now, let's write that down. T is tension, and we use it for forces applied from ropes, wires, chains, etc. Basically, anything that we pull with. And the reason why we like to use tension instead of an applied force is because things that have tension, so ropes, wires, chains, there's a certain maximum tension that if you try to apply more than that maximum tension, you are going to break the rope, wire, chain, or string. That's sometimes considered the test, or the test strength. Oh my gosh, I can spell. I've done it before. Okay. The test strength of a wire. Like a fishing wire usually has a certain test in pounds of force, meaning that if you try to apply more than, say, a 100-pound test line, if you try to apply more than 100 pounds of force with that line, it's likely to break. And they've tested to figure out how strong it is, meaning how much it can pull with before breaking. Okay, so let's do some examples of tension. A 2.5 kilogram disco ball is hanging from a single wire. Draw a free body diagram. Find the tension in the wire. Okay, well, let me just kind of draw a picture of the disco ball hanging from the ceiling. Fancy, so sparkly, yay. If I was going to draw a free body diagram, so I draw a dot off to the side representing the disco ball, I know that gravity is pulling the object down, so there is a weight force, which we call mg, and I can calculate that weight force by taking the mass in kilograms, 2.5, and then multiplying it by the acceleration due to gravity, 10 meters per second squared, which is going to give me 2.5 times 10, or 25 newtons of weight. Okay, so that's the force of gravity, or the weight of the object in newtons. Now, this disco ball isn't like accelerating up or accelerating down, it's just hanging out, chilling. So we can assume that the tension that is in this wire is balancing the weight. So I would draw a force up, call it T, and I know that it is equal to the weight of the disco ball because it is in equilibrium. It's balancing that force. So 25 newtons. And boom, I drew a free body diagram and found the tension in the wire. Now notice that this is similar to if the disco ball was on like a table. It's just we would say that that upward force, if it was a table, is a normal force supporting the object. And in this case, it's not on a table, it's hanging from a wire, so we use tension. Let's move on. You, 60 kilograms, are at rest sitting on a swing. Draw a free body diagram, and what is the tension in either chain next to you? Okay, well, let's draw a little picture of this, just so that you kind of understand what we're talking about here. Here's the tree. Fantastic. It's got a little leaf, and oh, it's fall. Yeah, okay. And you are attached or attaching a swing to that tree. Oh, yeah, perfect chains. And there are two chains on either side, hanging low, and you're sitting there having a wonderful day. Yay. Well, if I draw a free body diagram of you, I know that gravity is pulling you down, so there will be a weight force, mg, and that tension is holding you up. But there's actually going to be two tensions, which we could call T1 and T2. As long as this swing is level, meaning it's not like up at an angle or something like that, then we can assume that the tension is equal in both of those wires. And when I try to draw these two tensions on my free body diagram, I can do it one of two ways. One is I can try and draw the tensions next to each other. T1, T2. Just like that. But if I do that, I have to be careful to make sure that they are both touching the dot representing my free body diagram. But what I tend to do is not draw them next to each other, and instead I will draw them head to tail. So T1 and then T2. Now it doesn't matter what order they're in because they're being added. You can add in any order you want. Okay, so you should notice that T1 and T2 should be about the same length as the weight vector that you've drawn, because in this problem you're at rest, which means these two tensions are equal to your weight. Now I can calculate the weight force. I'll do it up here. 60 kilograms the mass times 10 meters per second squared, the acceleration due to gravity, so that's 600 newtons. And that tells me that these two forces, T1 and T2, they are equal to 600 newtons. T1 plus T2 equals 600 newtons. And as long as we can assume that T1 and T2 are equal to each other, then we know that each of them supports 300 newtons of the weight. And again, we're totally allowed to do that because this problem implies that the swing is level, and so they would each have a little bit of support for you. Okay, let's do another problem. You lift a 100 newton, which remember newtons are force, so 22 pounds, pounds are force. You lift a 100 newton rock up from rest with a rope. The rock speeds up at a rate of 2 meters per second squared. Okay, draw a free body diagram, find the tension in the rope. Let's start by drawing the free body diagram. The rock has a weight force down, mg, and I can, actually I don't need to calculate that. It doesn't tell me the mass, it tells me the weight. So I know that that is equal to 100 newtons. Okay, good. Now, whenever it does this, usually we want to find the mass of the object, or we're going to need it. So if I want to find the mass of the object, I take that weight of 100 newtons and I divide it by g. And g is 10 meters per second squared, so 100 over 10 is going to give me 10 kilograms. Okay, so I know the mass is 10 kilograms. We'll use that later. So you're lifting the rock and it's speeding up, which means that your tension is unbalancing the weight. And I know that on my free body diagram, I should draw a tension force that is larger than the weight. So that's the tension in the rope. Now, I don't know what this tension is yet, so I can put a question mark next to it. And that's what C and D, that should say A and B, and that's weird. And that's what part B wants us to find, is to find the tension. Okay, so this is a problem where we're going to need to write equations for net force to solve it. So remember that there are always two equations for the net force. One is net force equals mass times acceleration. That is always true, and you can always use that equation. So the mass is 10 kilograms. The acceleration is 2 meters per second squared. So I know the net force is 20 newtons. Okay, the other way that we can get an equation for net force is by looking at our free body diagram. So the other equation for net force is this. I know that the net force is T, which is positive because it points up, minus, because the weight force goes down, mg. Okay, so plus T because T points up, minus mg because mg points down. So now I know that the net force is 20, and I know that the weight is 100. So to find tension, all I have to do is plug those two things in. 20 newtons equals T minus 100 newtons. And so I know that tension is equal to 20 plus that 100 newtons, or 120 newtons. Okay, great. Let's do another problem. You are lowering a 20 newton, which 20 newtons is about 4.5 pounds of force, or weight, lowering a 20 newton bucket with a rope so that it is lowering at a constant speed. Draw a free body diagram and find the tension in the rope. Okay, so I'm going to draw a dot representing the bucket. I know that there is a weight force acting down, and that weight force is equal to 20 newtons. This is not mass in kilograms, so I know that that is the weight. I could find the mass. I just divide 20 by 10, so the mass is 2 kilograms, but we're actually not going to need it right now. So let's focus on what we do with the tension force. I know that tension points up, but I need to think, is tension going to be more than 20, less than 20, or equal to 20? And I know that it's going to be equal to 20. How do I know it's going to be equal to 20? Well, it says that you're lowering at a constant speed. Remember, constant speed or constant velocity means there's no change in the motion, or the acceleration is 0. And therefore, the net force is 0, because mass times acceleration is 0, that gives you 0. All right, so these forces are balanced. And I know that tension is equal to 20 newtons. Even though I'll draw a velocity vector off to the side, even though the bucket is moving down, it does not mean that there has to be an unbalanced force, because it can move with a constant velocity while having the force balanced. Let's do another problem. You are lowering a 20 Newton bucket with a rope, so it is speeding up as it goes down with an acceleration of 0.5 meters per second squared. Draw a free body diagram, find the tension in the rope. Okay, so same problem, except now you don't want it to move with a constant speed, you want it to lower with faster and faster speed. So the weight force doesn't change. It's still mg equals 20 newtons. But for this problem, we are going to need the mass, so let's just go ahead and find the mass. Remember, divide by g, which is 10 meters per second squared, so 20 over 10 is 2 kilograms. So that's the mass of the bucket. And I know that there is tension up. But here's the question. If I want it to accelerate down and speed up, then am I going to need to have more tension than 20 newtons or less? Well, if I had more than 20 newtons, then that would mean that my net force is up, therefore my acceleration is up, and the bucket is slowing down as it moves down. If I have less tension, then that would mean that my net force, the net of these two forces, points down, and therefore the acceleration is down, and the bucket is speeding up as it moves. So that's correct. I want the tension to be smaller than the weight. So the question is, how much? Well, to find that, I'm going to do what we always do. Use our net force equation, mass times acceleration. So 2 kilograms is the mass times an acceleration of oh, you know what? The acceleration is down. And if we're going to say that mg is down and negative, then that means I need the acceleration to be a negative 0.5 meters per second squared. So I would use negative 0.5 meters per second squared in my calculation. Half of 2 is 1, so the net force is 1 Newton. Now, what does that mean? Well, let's write our other equation of net force to figure it out. The way I write my other equation of net force is I look at the free body diagram. mg is down and t is up, so I would write t minus mg. Oh, you know what? Real quick. 2 times negative 0.5 is negative 1, so that should be a negative 1 Newton. Okay. So here's what we do. I take my negative 1 for the net force, and I plug it in here. Negative 1 newtons equals t, that's what I want to find, and then I have negative 20 here. So I know that tension is going to be 1 Newton plus 20 newtons, or 19 newtons of force, which maybe you were able to do that in your head once you knew that the net had to be negative 1 and the weight was 20. So the tension is 1 less than the weight, so that the weight is actually pulling a little bit more than the rope, meaning that the bucket is speeding up as it goes down. Okay, now let's do some left to right problems. Your best friend is in a frictionless sled. The mass of your friend and the sled is 60 kilograms. You pull your friend with a force of 120 newtons. Draw a free body diagram, then find the acceleration of your friend. Okay, so I'm just going to go ahead and start with the free body diagram, although this would be fun to draw. We're going to assume that this pull is to the right. And let's start with the weight. I know that the weight of the object, remember 60 kilograms is not the weight, that's the mass. The weight is m times g, so to figure out what the weight is in newtons, I take that 60 kilograms and I multiply it by, that's right, 10 meters per second squared. So 600 newtons is the weight. Okay, if they're on the ground, then that means there is a normal force. Maybe I should draw a little picture. Here's the sled. Here's your friend. Yay! And you are pulling them. Okay, so there's a normal force from the ground supporting your friend, holding them up. And I know that because your friend isn't accelerating up or accelerating down, that the normal force and the weight, they balance each other, they cancel out, they're equal. Okay, but what about the forward force, the pull? Well, so I would draw that force to the right, and instead of calling it an applied force, I would call it tension because it says you're pulling, and there's probably a rope involved. So T for that pull. Now, but first of all, correct, this is the free body diagram, good job. So how do I find the acceleration? Well, that tension is the only unbalanced force, so that actually is the net force. If there was friction, we would have to take it away, but there's no friction, so the net force is equal to the tension. Okay, well, how do I calculate the net force? Well, I can always find the value of the net force by taking the mass times the acceleration, and I said that wrong. Since the net force is equal to the tension, and I'm told the tension is 120 newtons, then what I can do is I can use this net force equation and divide both sides by the mass to get the acceleration. So the acceleration is the net force, or the tension, of 120 newtons divided by the mass of 60 kilograms. So 120 over 60 is 2 meters per second squared. You pull a 200 Newton box across a rough floor with a rope. Friction resists with a force of 40 newtons. The box accelerates at 1 meter per second squared. Draw a free body diagram, find the tension in the rope. Okay, so again, if the box is sliding across the floor, then for the free body diagram, there's going to be a weight force down, and it tells us the weight is 200 newtons, so I don't need to calculate it. The normal force will support the box, and I know these two are balanced. Then let's say the pull is to the right, so I would write tension off to the right, and you don't know what that tension is because that's what it wants you to find. But you do know that friction resists, so let's say that that's to the left. And the amount is 40 newtons. Okay, so the acceleration of the box is 1 meter per second squared, and we can assume that this is a positive acceleration. So what I'm going to do first is I'm going to find the net force. So I start with sigma F equals mass times acceleration. So the mass, we got to find the mass. To find the mass, we divide 200 newtons by g, 10 meters per second squared, so 20 kilograms. That's the mass. And then the acceleration I'm given is 1 meter per second squared, so now I know the net force is 20 times 1, or 20 newtons. Now, if the net force is 20 newtons, and friction resists with 40, then how much tension does there need to be so that I'm left with 20 after I take away 40? Well, how do we write that with an equation? We look at our free body diagram and we write a second equation for net force. T is going to the right, so I make it positive. Friction is left, so I make it negative. And now I can see if my net is 20 newtons and friction is 40 newtons, then the way that I find the tension is I take 20 newtons and I add 40. So the tension is 60 newtons. Great job. You pull a 10 kilogram box across a rough floor with a rope so that it moves with a constant velocity. Friction resists with 30 newtons of force. Draw a free body diagram, find the tension. All right, this one's so easy. The weight is down, the normal force is up, they're balanced. Tension is to the right, and friction is to the left. You might ask, why did I draw tension and friction the same length? Well, constant velocity tells me that those forces are balanced. And if the friction is 30 newtons, then that means the tension is also 30 newtons. Your dog is huge, weighs 400 newtons, and will not move out from in front of the TV. You attach 2 leashes to the dog and start pulling with a friend. You pull with a 60 newton of force, while your friend pulls with a force of 80 newtons. Friction resists with 100 newtons. Draw a free body diagram and find the acceleration of the dog. Okay, well, let's start with a free body diagram of the dog. Weight force is down, and it equals 400 newtons. The normal force is up, and the dog is not accelerating up or down, so I know that those two are equal, so I write 400 newtons. Okay, then friction and the pulls. Let's start with friction. We'll say friction is to the left, and it's 100 newtons. How do I draw these 2 pulls? Well, let's call this one T1 and this T2. Again, you could draw these 2 forces parallel to each other as long as they're both touching the dot. But what I like to do is draw them head to tail. So T1 equals 60 newtons, and then T2 equals 80 newtons. Okay, so now I can work on my equations of net force. I know the net force is equal to mass times acceleration, and that's actually what I'm going to want to find here. So if I divide the net force by mass, then I'll get the acceleration. Let's find the mass of the dog real quick. Can you do it really quick? If the weight is 400, then the mass is 400 over 10, because you're dividing by g, so 40 kilograms. All right, so the acceleration is the net force, which we don't know, over the mass, 40 kilograms. How do we find the net force? Well, the second net force equation is not m equals a, but instead we get it from our free body diagram. The normal force and the weight balance out, so they don't contribute, but here I have T1 and T2 to the right, so I'd write T1 plus T2. And then friction is left, so minus friction. I don't need to rearrange anything, I just need to plug it all in. I've got T1, 60 newtons, plus T2, 80 newtons, minus 100 newtons. 60 plus 80 is 140, minus 100 gives me a net of 40 newtons. Now I can find the acceleration by taking that net force of 40 newtons, dividing by a mass of 40 kilograms, and getting an acceleration of 1 meter per second squared. Congratulations, this video is done.